Should be recording. It's not recording. Is it written down? Yes, it's recording. Yes. So this video should not exist. So again, the trial topology model is the same thing because you have a yes, I want to download it. Am I sure I want to download it? Is there a nil state? Like I said, you have a preset there. By Adobe gets one has a preset. So basically, you got the trident. So you got the dependency held. So you got the diamond because the B1 and B2 are trying to download to some computer C. But they uploaded via consensus and download the model. So basically, you're gonna have three servers for this. First, you got your local server, and you get a remote one to that. So you got the same thing in a mirror server to the servers online on a computer and run well. They can recover it via Observer Consumer, and you get the other one, the other two server that holds the same thing like a mirror, but not the one you manage directly, the one you upload to via the remote protocol to the one. So you have one you keep locally, one you keep online, and one you keep archived or some kind of someone when you keep active online. Strike an effort. Which I'm trying to do. So you get a live. So basically, you have three ways you do it. You get a local repository for like some kind of dependency, some kind of library, but then a local one in your computer, local git git-raf, which stands for regulation of firmware, and you get the remote copy of that one, the timestamp date, metadata alpha. You can always download that one because the same one, local copy if you want to just keep it updated or live update. But there's one more that's the static, less updated, but most is 100% stable via the SemverX version X YZ. Because the major patch the system must resolve itself autonomously via Sparse topology, because it's like a consistent system. It's not a typical. Basically, you're gonna use it to update whatever the MMUKO systems is. That's the idea. You never need to ask for the update because you're locked in for life. That's the idea. Here, you're locked in when you get your MMUKO PC. So how does it work in practice? So we're showing like the transition. So if I say yes or no, that's a binary question. But if I can say no, I'm not sure. No response means I'm not sure. Because that means I have no time to respond, so I bound the time. Or I have no space to respond. I can't give you consent even. Or say yes, because my character encoding is not canonical. You don't accept my my Chinese character in your my Chinese character, my Chinese word for yes if I'm in England, and vice versa. If I'm in England and China, I can't put a Y, yes, Y, because I don't know if I have to put the right Chinese character. This kind of can control problems. So the solution is this for me. So you get something like called A-star scoring, which have a full defense. So basically, you get Dijkstra algorithm, which is like the second fastest A-star scoring. And you get A-star scoring itself. This is the fastest O1. So basically, it's consistent and conscious. So it really knows. It doesn't have to run it. So it's all bound to log one. O1 complexity for dependency. A is a state, A is a library, A can be anything you depend on directly or indirectly, because if you have a B, C using A indirectly, it's a dependency. But you mean to prune out this dependency you don't use. So pruning is like ensuring you only download what you need in your laptop. So basically, if I'm using B and B2 contains A, but via some kind of isolation or separation question, then I get A. Without to get B, I get B2 because B2 has A. It's homogeneous. It's heterogeneous or homogeneous library, because basically B resolves A by itself because it already contains A in some kind of isolate system, some kind of container. So you don't have to download A again on your whole system. Host life simulation models with the same thing via consensus. So what's the scoring? So you get A-star algorithm for dependency. It's just O1. You just download. But that's really not good enough for trying to. So you get the space complexity. Basically, if you get anything under log n, over log n, complexity, like one active download over log n, then the system is broken to me. It's not conscious, it doesn't work. You need to rebuild it, repair it, renew it, because you have to show that there's log n because half the time over the linear protocol is the standard specification for it. So when we say the words like n, there's no log n is just too much. So you want everything in the worst case scenario to be log n and everything to be already known at all n. That's the policy I'm trying to enforce, which works now. So how it works? So the weight of a graph is dependent on the trinomial model. For example, the 1 0 0 0 1 0 1 0 0 represents the state where 1 is a yes, 0 is a no, and nil is a not sure. Unsure and homogeneous model, but it's a homogeneous model only because the data is structured enough and you don't need to separate it yet. So, for example, again, so we get so the yes basically for this matrix you get no polarity even. So if I give permission, then consent, then consensus, then I've done it. Agree to disagree. So if I have 4 yeses and 3 nos and 2 nos, then I've given consent, consensus, consent. Because if we have a maximum of 4.5, basically I've given consent with this model, no consensus, but because it should be 4.5 to over 9, 4, 5, 6, 7, 4. 4 yeses, 4, 5, 6, 7, 8, 9. 4.5 for consent. This isn't consent bound because it's not even halfway. This is like a permission agreed. So if I have some kind of dependency, it will not resolve with A star scoring. So A star scoring is A star algorithms, but for sparse modeling, because you get this thing that reposes itself based on diamond automatically. It's automatic, it has to resolve itself without being a human trying to do it manually, or like writing more code to do it. Because it's kind of topology that's isomorphic to the original state. So you can have a new model to give you that artifact, without going to dependency hell, which is kind of the invariant property, no dependency hell. For example, the weight yes is 0.14814. Now 0.1814 is not good enough. It's just a yes. How sure I am my permission. I'm sure I have permission. But if I say no, 0.0704 and nil 0.1 recurring. Why this matters? So how does this work out? So you get 4 divided by 9, which is how it works. So 4 divided by 9 is my consent parameter, and then you get 9 3 divided by when I say yes, and then you get 3 divided by 9, which is my no. I'll get nil of 0.1 recurring. This is 0.1111, which is what can be the weight of the node. Now, if you use a Larian edge bound, this will be the weight of the node in an edge for how sure I am, which brings me to my next point. Certainty on uncertain duality, density matrix. So, if I'm sure something, I shouldn't be downloading it. I shouldn't be thinking about that. Because it doesn't pull for that remote thing. Because I'm not sure I depend on it. It's basically we can check the mirrors to see whether they're right. We're gonna tripartite consensus system, which is actively based on your input. If you're part of kind of a network. Why this really is the thing for us. So I don't know what to switch analogy yet. I just wanna come back to the other one. So you get the union model. So you get what do I call it? So yes. So you get I think I have to write it down again. So you get the permission manager, which I don't want to show you yet, but I think I have to show you because I can't even find what I was looking for. Yes. Let me show you the permission one instead, because I can't even find what's looking. So you get this is like this is a model here. This is like the permission via read, write, execute. It's based on biological one, so it's like a tree. So you can see here if you have a x of write, you have 1 write, 2 write. So you have to have a full write permission. You have to have to basically to write to some kind of local system. You need 2 writes. So 2 writes to write to the local and the remote one. So you need 2 writes. Basically, it's a rotation of AV to be a Sparse matrix. For example, there are 3 epsilon states, 3 epsilon states, 3 no epsilon states, We don't know what's an option or not. So it's like a no, yes, no, but there's a nil. We don't even know. So it's 3 times 3. That's where it comes from. So you get 3 known on surety, and you get 3 unknown. Or sure, and get 3 we don't know. We both don't know. Maybe it's a new system that's non-standard, non-compliant, non-enforceable, non-enforced. Which trying to mitigate. So or the nil. So this is like a nil matrix. So it's a functor of nil. So if I have this heterogeneously, there can be models is yes, no, nil, yes, no, no, yes, no, yes, no, nil, based on the inverse one. So how does it work? So you get say you want to open an image now with Rift. Rift, if you go to R open, github.com/OBINexus, R, Romeo, R for Romeo, O for Oscar, O for P for Papa, E for Echo, and N for Nen, neck. So you get 0 to 9, which is standard one, and you get A to F, A to G. No, 1, 2, 3, 4, 5, 6, 7. 8, 1, 2, 3, 4, 5, 6, 7. H, 8, 9. So you get 8 to I. 1, 2, 3. Basically, you get 16 minus 9, which is 8. So you get 1, 2, 3, 4, 5, 6, 7. So you get A to G. VX is the multiplication. You can get 0 to 9 on the x axis because there's heterogeneity, so things that are, but they're also homogeneous because they're used in both ways. And you get the -1 based on the coding layers of it via the triad model. But the goal is just never lose the information set via the margin of miss. So if you implement a program that opens an image of a program architecture, you have to have the right permissions to it via the hexadecimal. So you get the R syntax, Rift, A to Z, 0 to 9. But this is like the R, so it matches anything 6 times. 6 times. This will give you actually there's one there. So this is the one here. So you see that's basically like a C amplification of it. But you want to open it for permission. So you have permission to open up Windows. So if I change the Tmod position on Linux, so basically if I switch context, Tmod plus 9 plus X what 777. I have read write execute permission. But this is not the same as Windows one. So it should be the same. That's the idea. Or if I do to plus X, I have all the permission, plus W write or plus R. So how this works in practice. So if I write write something, if I write to a file, if I'm able to open a file, if I'm able to read a file, I'm able to open it, and then write to it, read it, right? If I'm able to write to it, I'm able to execute it, like I change the document, update it, or execute it directly. So if I prioritize my right to read it, I get I don't need permission. No permission needed. I get consent. But consent equals permission in this framework too. So after sure I have consent but no permission. So you can model like a read, read. So you can have like one read. For my one read, there are two. For my one read, there are two rights to consent. So that's why the 2W comes in. 2W. But for full access, for my one read, there are two rights you need via consent, and then you want two. You want two. Then you get for the full one. You get. I need two reads. One right. Basically, two rights. On one read. Two rights on one word for consent. For execute, I just have to change this executable format. So I get the two read, one write. So two read, write, one write. Because if I can read a file twice, then I already change it because I don't need to open it again to write to it to change permission. So because I already hold the permission of consent. So I really need it twice. So that's because I don't need to open it. So that's the idea of the matrix. So in my view, so basically, to do it properly, you have to do it properly, do three properly. So you get like for every time I read, I get a write permission and a execute permission. On the left node is write, and the right if it is execute. So but the execute is not the IOTA state. Basically, they don't want to set the IOTA state is just main default. So if I'm able to also read the file or attempt to read the file, Best to balance out with the execute permission. So if IOTA state is read, the inverse IOTA state is write, because it's two dual IOTAs based on the maximum equation threshold. So I'm doing really the matrix works like this. So x1 x read, write, execute. Read, write, execute. So it's like biological. So you can have like I think about biology, two codons, basically just if you go to my biology, which you see there, I don't know specifically. I have two R. If I read once, X I get to read Y. I have two R. If I write once, what am I doing? I'm reading two. Basically, if I write once, I'm really reading. So I get my two R. I get my if I'm if I'm writing, if I consent already, I'm writing. Then I have to just read once, one read. But one read equals one iota write. So I don't need to open again if I'm in a state of, So if I one read, I get one iota. So that's like the default. I'm ready to write it automatically. If I have one SQ permission, I've got to the read. I have to go to read, write, two read, one write, and one execute. That's the idea. And then you get to one read. If I'm reading once, I'm trying to write. So if I'm reading already, I'm trying to write. I go to read, write. So I have to go to via two reads based on if my local one is read and my live one is read. I have to go to my room one is already read. So if my local one is already read, my room one is read as well. Then my read write then I have to write again to my repository. So I have to get one read permission from my local and one two read permission local and one write. Permission. If I'm already local reading the file and I want to write to it live, I go one write, one local write, and two read and write. One read, one write. So you get two write, one read. One write, read, one write. Because it has to be isomorphic. So one read, then one write. And then to execute it, I get all of this. So I get two read, write, execute permissions. And then I get the two reads, two reads, two reads, two writes, two reads, two writes, to get one execute permission on the server in the real world. And then I get the same thing first. So I get the same as you get two writes, two reads. So for me, just read on the server. I get to execute it on the server, not local. I get two writes, reads. I get one read and one execute, one R execute, and then basically it's like a DAG. So I get if I want to write it and execute it automatically on the server, I got to first read it first. I get one read it first. I have to get one read minimum and one read and one write because I have to read it then execute it. And then go to one execute for server one. So this is a kind of one. So find a one for to execute on the system. I have to get a read, write, execute. One read, write, execute permission on local one, and I have to get another read, write, execute permission total to give you the and that'll be the uploading the pushing to the local from local to remote repository and remote to server repository, and that's the idea of the matrix. So it's based on the permission manager of some kind of opening some kind of author locally. If you have consent or not via consensus modeling. But there's one more thing I want to address before I do this. I'll leave this video now and save down this video. It's kind of like it's same basically what's same for the light switching, but the light switching is like the same thing. Here, I don't talk about light switching here because I really I'm not done with it. I'm just gonna try to find what I came to do. So the light switch here is here. So I just like come back to it later. The principle is basically the light switching one is nobody want to do now. Yes, the scoring mechanism. So what I mean by scoring, so I did get it here, yes. So you get the scoring of it. So what is the A-star scoring? So the A-star scoring is log 01 scoring via Hamiltonian pump. Now Hamiltonian resolution is depth first, right? So depth first you go down the layers, but you don't want to keep going down. So you have to prioritize propagation. so you know where the auto resolution. So yeah, I don't like Hamiltonian resolution. Maybe some sparse mode can do it, but I prefer the best one in my policy. My thing is edge bound. It's edge bound bottom up, like a first thing, first out, because you risk looking with a graph model, and that's why I prefer. You don't use over Hamiltonian, but we get Hamiltonian there as the non-default. So I use the state or resolution, based on actual resolution. So which is sparse modeling. So the first in first out model is goes bubbles up to source code error, which is why you learn because you learn is the bottom of starts from where the error is, where your code is, because it's just a code that's the problem. In most of the time, in my view, you're not understanding some new concept or not. So that's my idea. So you purposely for me in my framework, I prioritize. And for every one dependency I resolve, I have four dependencies. I use 11 graphs to resolve edge band graph. Why? So think about the half rule. Half rule. If you have two halves problems, two halves, two. If you have one big problem in half, if you have one problem and you half it, you have to you solve the problem by divide and conquer and divide and merge. If you divide the problem, but divide and conquer and merging can conquer and merge the problem. If there are two solutions, we can divide it in two. So it's a bit of two, but that's like four. So if you divide twice, you are what making it four. So basically, you want to scale double the problem solution space by two. If you share the problem in half, so that'd be two half times half. You get a quarter of the problem solved. By a telemetry system because half times half is just a problem model. So that's the idea here. So if you have one half, you get the one solution times 1.5 plus 100 1.5, then you get two halves is one, and that becomes three, and then one plus one is two, so you get two plus one equals three, and the thing will be resolved via some kind of a binary classifier of epsilon states, via sparse modeling. But Eastern current is really this. So, for example, you have the range. The range is nil. So, like think of it. So you get the median. The mean is what does it mean? The mean is the biggest minus the biggest divided by the smallest. The mean, the biggest. Basically, the mean is the most common number, the biggest, all the numbers added up. So basically, if I have nine, all the numbers added up, I get 4 plus 3 plus 2, 4, 5, 6, 7, 8, 9. So I get 9, 9, divided by the mean, divided by 3. So the mean here is 9 divided by 3, and that'll be 3, because you get 3 average to score. Now, this average represents like a statistical average that can be used across all domains. So because like you get like a consent model. So basically, trying to find values. So you get consent. This makes sense. This is what it is. So you get permission, consent, and consensus. 1, 2, 3. This is what it is. So basically, everything in this room can be under the 3 model for sure. But for example, the median, the range is the range of the system. So the biggest minus smallest, 4 minus 2. So my yeses, 4 yeses minus 2 nils on shows is 2, and then what? 2 divided by 2 divided by 9, 2 divided by 9, 4. Basically, this would be the range. The biggest minus the smallest. So sorry, the biggest minus the smallest is 2. But basically, you get 4 minus 2 is what? Is 2. And then the biggest is 4. And the 4 yeses, 2/3 over 2. 2/3, 2/3 over 3 is what? The range. And this would be the consensus for version system. So this would be like the median, the range. The range to cover that it covers the consensus of like some kind of telemetry insight. Some kind of error-prone telemetry system that models kind of how the system behaves in real time. Basically, if you have 3 over 3, this can be represent the consensus is just consent. I've been consented via the range model. So that's what it means really. And you get the range, and you get the other one mode, the most common number. So the most common is yes. So that's like the 4, and then you get the range, mode, median, range. This is historical average over OBINexus differential system. Mode, median. So median is all the number in order divided by how many there are. Now the median in this case would be two nils, three and three, 4. That would be 2, 3, 4. No, basically the median will be 3 because nil nil cancel out nil. Then go every nil will cancel. So 1 nil cancel 1, 2, 2, 3, 3, 4, 4, and the nil will be 0. So the median will be 0, which will be null. So this will all be the default IOTA states that you measure for consensus modeling. Because if you download something, you want to be sure as you download it. No matter the sparse network, you have a tripartite graph that can check this via the polyglot semantic version X model. So last but not least, I still got time. Anyway, I can upload it now and I'll start a new video. So last but not least, this is how it works. So you get it's basically like the biology codon system. You get like enzymes rebuild. If you can rebuild something, you can renew it. The same thing. If you can build something, you can renew it. If you can repair something, you can destroy. You can break it in half. Because they're just conjugate inverse operations. And then you get if you can repair, destroy something, you can create something too. It's not like a new concept I'm trying to invent. This is a tripart biological idea. So if you don't really understand this, think of this as an operation for consensus. Let me write it down because you guys can consensus bound operators. If you can rebuild it, you can renew it. If you can renew it, you can rebuild it. If you can destroy it, you can create it. If you can create it, you can destroy it. If you can repair it, you can break it. And that's a tri-pattern model for operation. If you don't get anything else. But the goal of the scoring, again, A-star scoring, is to have the space complexity. When a human is not actually fixing the code to be O of 1 via auxiliary construction and with active resolution in real-time world. And so basically you get space over time, it's O of 1. O of 1 times O of 1 is just epsilon, so it doesn't take any space or time to do it. It just does it. It just does it. It doesn't really need people to do it because the A-star scoring is A-star is the fastest, most optimal algorithms that track a state, and it just catches. So you observe basically when you observe the state, you are at doing it. What is login? So if it's login protocol, you are login. That's half the time, but login of log O1 of 1 is just login because there's no need to store it. So if your algorithm takes even n, the protocol is O1, and that will be n. So your code is n to download. So whenever you push something and you fetch something and you download something, it doesn't really do anything to the system because the controller is just A-star scored. If it does deviate from this kind of a trial model, then the system is broken, and that's what I'm trying to enforce it. Based on mechanical up-down switch access polarity. I can still have myself time. 45 minutes has not gone by, Namdi. So that's like the idea here. So you can rebuild something, you can repair it. They're different. They're not different. They're just isomorphically inverse. Also, example. One last thing. I've already done it here, but I can't find it here. Basically, I just try to get it here. So you see this here? So this is kind of so you get like an intersection of the human rights political control model. So you get so you get like a light of it. So you get a bit of it. So what I mean, so basically, I already worked out here. Yes, it's here. So what is it? You get so the same thing for you. So if you have some kind of technical specification on the US, down is on for light switch, and roll out right you get up for the US. So up is just basically US on is you can off, you can't have unless you switch some kind of a component you have via hot swappable logic. So you try to resolve for that locality you're in, or that sure basically some kind of a master switch you can make. And this is a model of a secret 0 0 epsilon 0 is epsilon matrix. You get 0 times minus epsilon is minus epsilon. 0 times epsilon is epsilon. So you get up down. So this is like so you're off US a negative epsilon is my on my off epsilon. So you get that kind of model there. So and your my off is your, so these you have to rotate the matrix, polarize it correctly via the trinary system. So are we working out how you're about quick to do it now? So basically you got the row 1 too. So the row model is like the same thing, but it's the same information but in a different order. It's like no, it's same information. So you get 0 1 0 0 in the vertical matrix, and you get the row 1 1 0 0 0 or f0 or epsilon or nil nil, nil. But it's all information of nothingness. But the thing is, you have to rotate it, transpose it, because you are changing the mechanicalization of it, final system, because the symbol of atomic rotation to it. Because it matches to the system, the information, how the information get processed. If you have a matrix and you can process it in like the rows all at once, that's what you try to equip here in this model. That's the default I used to say. You have a start point for it, because the row is going basically you have a row something is going in a linked list where you get can put it in the one by one sequentially. But you can put it in a pattern too. If you see like one thing, you don't need it. Or you can process the opposite. So it's basically think of it like you pop if you don't stand it, you get like a 0 0 1 0 example. So if I read from the right left, I'm processing the leftmost bit, the rightmost bit. So if I'm reading from right, I'm processing right, so that'll be 0 comes pop 0 dot pop. Pop will be the first one I get 0, and then the next one will be 1. So I get 1 this time, and the next one I pop, I get 1 1. So basically I get 1 0 0, then 1, and then 0. But this one is not the same as the conjugate one. So if I try to read if I have the row, I get the column 1 0 1 0. I can't even like pierce this one. So if I try to read this 0 is the same as the epsilon, negative epsilon. So negative epsilon is here. But that's the conjugate one, because you have to start here. So the 0 and then the negative epsilon here. So it's corrupted. It's corrupted by design. Because it doesn't know how the structure of a list is. It's a two lists. But just think of these streams are duplex string, because I can only singlet streams if you don't get what I'm saying. This is a stream of information I'm trying to process at the time. But the structure is two registers. So I can process the epsilon 0. But I can't process from the side because it's not aligned with the one there is. So for this solution, you get the read write permission manager. So you get canonical state of minus epsilon to minus epsilon on the x. You get read write. Okay, so you get for all the states to be shared, I define a epsilon matrix. So minus epsilon, I start minus epsilon, and that will be the same as epsilon. Epsilon. So that'll be minus E or E. That'll be the same matrix. And this will be the row of of the system. So for example, the matrix here I have is 1 1 times 0. Yes. Oh, sorry, got to hear. Sorry, guys. So basically, my solution, guys. I'll try to look at it. 3, 2, 1. You see it? 1, 2, 3. That's the solution here. So, the US on basically, I have row 1. Row 1 is on, and column 1, row column 1, row column 1 is equal to column 1. So row 1 is equal to column 1. That's the same thing in the model of the canonical off states. Basically you're trying to get it off to on. So when they're both on, you get a row column 1, and on the UAK and US must align via the sparse model. So and then you get the on state like row 0 for UK is a row 0 column 0, and this is the matrix. No matter you change this canonical data, the IOTA state for on is like a row 1 is you get 0 0 row 1 for US, and then row 1 column 1 for US is the same as row 0 column 0 for US, which is the same for on, but the off is like all the epsilon. So you get the epsilon, so 0 0. So you get like a row 0 of row 0 column 0 for US is off, and you get what for UK you get row all the other ones is it row 1 column 0, that will be off for US. That's the user state. You know, there are two stations to map. Depending this is master switch basically. This is master switch. To turn it on, you have a master switch to kind of do both of this operation without fragmenting the whole trident system for epsilon resolution. Okay, thank you guys. I'm gonna upload this video now.